Good morning, students. So myself, Dr. Ajith K. I teach physics in Department of Physics, National Institute of Technology, Karnataka. Today we are going to talk about and discuss an experiment called Helmholtz Resonator. And this is a very simple experiment which you can in fact do it at your home. Take a bottle like this which should have a neck. Even a Coke bottle or a Mirinda bottle, all these things will work. But you should have a neck, and there is a main part which acts like a cavity, and there is a neck, and you can see here, you can blow air and you can see a sound. Listen a sound, it acts like a whistle, right? Now, if I fill some water here, let me fill some water, and I repeat this, you get a different tone, right? Now, if I keep doing it, you can see there is a change in the tone. That means you are changing the frequency. One more time, so we need to do this, and right. So each time when I fill the water, what's happening is you are actually changing, reducing the volume of the air column which is here, right? So if you have a sense of sound in music, you know, when I go it the first time, it was a flat noise. When I put some water, when I decrease the column, you can see that tone becomes sharper and sharper. That means frequency is increasing while you decrease the volume of the air column. So that means when you decrease the volume of the air column, the frequency increases. They have an inverse relationship. This is what we are going to verify in this Helmholtz Resonator experiment, and we will verify this relation. Using this relation, we are going to find out the unknown frequency of a tuning fork, which I am going to tell you now what is a tuning fork, how do we do the experiment, and all these things I will tell you. But I request all of you to do it yourself, and maybe in the theory part, which I will record it separately, and there I will tell you how to calculate the resonant frequency of a bottle which is filled with some water. So resonance means a matching of two frequencies. I am exciting here, right? I am doing an excitation by blowing the air inside some folds, and see, when you blow air, it's just like a white noise. It has so many frequencies. So one of it is picked up by this Helmholtz resonator and it gets amplified. So that's what the resonance at the point it happens. Okay, so this is what we are going to do it in a little sophisticated manner, and we are going to do the experiment, and there are a lot of applications for this. For example, if you go to a auditorium or a studio where you can see that there are perforated absorbers kept all around, you can see that there is some kind of sheet with so many holes, and that is basically a Helmholtz resonator. And in fact, in cars and all, to reduce noise, they use it. And so I request you to find out, look around materials which is available, what are the applications of the Helmholtz resonator, and you can perform this experiment. And if you have a brother or sister, you can actually impress them by doing this. Okay, thank you. Now we will go to the experiment. Good morning, students. So we'll come back to the how practically we are going to perform this experiment in the lab. So here we have a set of tuning fork which is given to you, and I have actually 5 tuning forks. Tuning fork is actually manufactured to vibrate in a particular frequency which is written here. Maybe here it is 286, you have 384, then we have 460, then the 256, then there is one tuning fork whose the frequency is we have covered with some tag. And the aim of your experiment is to determine the frequency of this unknown tuning fork. So basically tuning fork is designed to vibrate in a particular frequency. There are 2 prongs and there is a stem, there is a base. These are the parts of tuning fork. So when you excite the tuning fork, hitting gently on a substance which is not so hard, like a piece of a tire, that's what we are using here. So when you excite this, the prongs vibrates and it creates the, there is a pressure and rarefaction region around it that actually create a longitudinal waves. And we have a bottle which is filled with water, and you see that bottle is also having a neck. Okay, so up to the neck I have already filled the water. Okay, the water is filled. Now I am going to create an air column, and which is going to resonate with the frequency of the exciting frequency of the tuning fork which I am using. So this is what we are going to do. So how do you change the air column is the volume of the air column you can vary by taking out the water out from the bottle. The bottle, down there is an outlet pipe, and the pipe is controlled by a valve. If I release the valve, then you can see that the water will start flowing out. You can see the water is flowing out, and this I can control by tightening it or releasing it. You can control the flow of the liquid, and when you start doing the experiment, you take a tuning fork. And you excite it and keep it on top of it. Gently you hit and excite, you keep it. You remember, I have actually started allowing the water to flow out slowly, so that at some point of time you can see a sound which is very loud, and you can hear it freely, and it will start appearing, and slowly it will fade, and it will reach a maximum point, then it will fade. So that maximum point is where you want to look. Okay, that is the resonance point. So you repeat like this. So you have to keep on trying this. So no sound. So actually the sound coming portion I am going to show you separately now. So this is students, now you can see I have been keep doing it. So at one point you can actually hear the sound. See, it's slowly going, fading. Now it's gone, right? Now it's gone. Now you can see that some little bit of water, you pour it back and fine tune for the maximum. See? Now you got the maximum point. Stop at that point, take out that water, all water collected, pour it, and you can see this is 150 and above that 155. So this is actually 155 ml of water is removed from the bottle, and so the volume of the air column is actually this 155 ml. Okay, so this is, I have done it for only one tuning fork, and you have to repeat all other 4 tuning forks like this and find out the resonance point and corresponding volume of the air column you identify, and you have to note it down in the record book, and the tabular column and other things I will explain in your theory part of it. And as I told you, there is frequency square times the volume of the air column which is resonating is a constant. So this relation you will use it, and for an unknown frequency, the tuning fork with an unknown frequency whose volume you will calculate, and when you plot the graph between the volume of the resonating air column on the y-axis and the 1 by frequency square on the x-axis, you are going to see a straight line with a almost 45-degree slope, and because that's a constant, and you can see that while performing the experiment, you will identify the volume of the resonating air column corresponding to unknown frequency. You take a straight line, draw a straight line which intercepts your, the straight line which is obtained by n square is constant, where it's cut, and you extrapolate down to the x-axis. That will give you the 1 by nx square there. Suppose nx is the unknown frequency, you will get what is 1 by nx square. From there you can actually calculate what is nx. So this is what the experiment you are going to do. There are some tricks and other things. See, as I told you, when you read the theory, you know that the frequency and the volume is having an inverse relation. So where to start? You arrange the tuning fork in the ascending or descending order. So from where to start, you can actually identify it from the relations, and there are some tricks like this. When you do practically really come and perform it. Okay, so those things I can tell you more in the theory part of it, and I will stop here my video. The remaining part is a presentation which you can look for the theory and some other tips to perform this experiment and things like this. And very interesting, as I told you, this modeling of, this is also, one second. So you have this bottle which I was talking about in the beginning of the experiment, and Helmholtz resonator. Modeling is a very important part of physics. So how you model this is very important. So you have a neck here. The neck, there is some air molecules are there, some air is there. It has got a mass. Okay, so it's not actually the mass in the conventional sense. It's called acoustic mass, and you have a cavity here, and this this cavity will, when this air in this neck pushes down, cavity, the other air with this, even otherwise, if you don't excite it, the pressure here and pressure atmospherical is almost same. Okay, when you excite it, the pressure with which the neck, air molecules in the neck which it pushes, okay, and there is a back reaction, reactive force acting on that particle which is in the neck, which is like something like a spring. So you have a mass, you have a spring. So it's something like a mass spring system, and that will vibrate with a natural frequency, and that frequency, when it matches with the exciting tuning fork, you will have the resonance. This is the way it models. So this modeling part which I am explaining you in the presentation. Okay, so thank you, and have a good day.